Okay. Right. So last time we started our last topic, which, as you can see by the date at which I started it, won't take very long, and that has to do with velocity constraints. Also known as non-holonomic constraints. Okay. And last time what we did was we just gave two simple examples, which I'll quickly reproduce here. Okay. And so for we had this just a disk rolling in a line, and it had a coordinate x and a coordinate theta, and then we had our rolling disk example, which we looked at before, and this, well, the way I labeled my coordinates is I had my angle going this way, phi, and then a rotation angle like this, theta. And last time what we did was we derived the constraint that in each case, the point of contact of the body with, in this case, the line, and in this case, the plane, was that on the velocities of the system. And so because I'm going to use these today, let me just remind ourselves what those are. So for this one, the constraints on the velocity were that x dot is minus rho theta dot. Okay, and rho is, in both cases, rho is the radius of the disk for both systems have disks. And then this one had a velocity constraint, which was rho cos theta phi dot, and y dot is rho sine theta phi dot. Okay. All right. Okay. So so we want to think a little bit more generally now about this, and to do so, so the point is that in each case, this defines on the set of velocities at each configuration, it defines a set of constraints that the velocities must satisfy, and in each case, the constraints are linear in velocity, right? So the velocities all appear linearly in these formulas, and so therefore the set of x dot theta dots, and in this case the set of x dots, theta dots, and phi dots, which satisfy the equations that implies that the set of velocities that satisfy the constraints are a subspace of the tangent space at that point. Okay, and so that leads to the following definition. All right, so let's work in the mechanical context, although there's really nothing, once except when you're looking at examples, there's nothing necessarily mechanical about this. We're going to consider an interconnected mechanical system with a configuration manifold Q. Okay, so a non-holonomic constraint right? So this is a common terminology. It's not the best terminology for various reasons. And this is, I think, a better piece of terminology. So a linear velocity constraint is an assignment to each configuration Q, okay, a subspace dq, okay, in the tangent space at that point. All right, because that's exactly what these conditions in the example are giving me. They're defining a subspace as being the set of velocities which satisfy those equations. Okay. All right, so attributes of linear velocity constraints. Right, so right now this is very general, and in practice, linear velocity constraints have all kinds of properties. Okay, so attributes of linear velocity constraints. Okay. All right, so the first thing that you may want a linear velocity constraint, first property you might want it to have, is that it should, these subspaces should fit together in a nice way. Okay, and that's, so there should be some kind of smoothness. So let me say how you would define that. Okay, so a linear velocity constraint. So let me abbreviate it like so. D. All right, so D is going to be a subset of the tangent bundle, right? So at each point it's a subspace, is smooth if for each Q in Q, there exists a neighborhood U of Q and C infinity vector fields. And let's say there's finitely many of them. They're in all the examples we're going to look at, there'll be finitely many of them. Okay, so these are vector fields on U such that this subspace D sub Q is spanned by the tangent vectors corresponding to these vector fields. And this should be true for every Q in U. Okay. All right, so I can find, so the velocity constraint D is smooth if I can find smooth vector fields that span the subspaces defined by D. Okay. Now those X's may not be linearly independent. Okay, so it may not be the case. So these things may not be linearly independent. I'm only asking that they span. Again, in the examples that we're going to see, they will be linearly independent, but it's not part of the definition. Okay. All right, so that's what it means for a linear velocity constraint to be smooth. Okay. Another common feature of these kinds of things is what's called locally constant rank. if for each Q in Q, there exists a neighborhood. Okay, so the neighborhood is where local E comes from. Okay, good. See how that worked. Yeah, so sorry about this. Maybe here, sorry, a Q here and Q's here, and they of course can't be the same. So let's call these Q prime. Okay, and I'm going to have this. Well, we'll just keep doing that. Okay, locally constant rank means for each Q, there's a neighborhood U of Q such that the dimension of dq is constant. And this should again be dq prime. It's constant for Q prime in U. Okay. All right. All right, so these are two properties that linear velocity constraints can have, and we're going to see velocity. All right, so let's then look at our examples. Okay, so the first one, so I'm going to sort of indicate how you sort of work with these things. Okay, so what we're going to do is we're going to write the linear velocity constraint as a linear equation. Okay, so write the linear velocity constraint as a linear equation. Okay, and in the first example, that amounts to, so you're going to write it as, like kind of a matrix equation in x dot and theta dot. Okay, so in this case, the coefficient of x dot is 1 and the coefficient of theta dot is minus rho. Okay, so the matrix that you're going to stick out front here is 1 and minus rho. Okay. Let's see, it's locked up again. There we go. All right, and so what we're going to do is we're going to find vector fields like this that span D. Okay, so to find vector fields that span D, basically you take that linear equation and you find a basis for the set of solutions. Okay, and so what that amounts to is finding a basis for the kernel of that one. Okay, So, now we're back in, first year linear algebra solving linear equations, but in these particular cases, they're very simple. Okay, so we find a basis for the kernel of the coefficient matrix. Okay, so you need to find a vector field. So it's going to be a linear combination of d by dx and d by d theta, which satisfies the equation. And so in this case, there's only going to be, the kernel is going to be one dimensional matrix. And so as long as it has full rank, which it does, the rank is 1, then its kernel will be one dimensional. And so there's going to be one vector field that spans it. And it's going to be rho d by dx plus d by d theta. Okay. Right. So that satisfies, there it is. So that satisfies the linear velocity constraint. Okay. Right, and so the point is that dq in this case is indeed spanned by the single tangent vector. All right, so that's that example. So the other example, again, we're going to write a matrix equation. And it's going to be a linear equation in x dot, y dot, theta dot, phi dot. Okay, in this case, there's two equations. Okay, and so the coefficient matrix in 0, 1, 0, 0 cos, sorry. And so it's minus rho cos theta and minus rho sine theta. Let me just, make sure I got the, signs right. Okay. All right, so now again, you need to find a basis for the kernel of that coefficient matrix. And that coefficient matrix, it's in a nice form, right? With, you've done row reduction, there's leading ones, all that stuff, right? So that is easy to find a basis for the null space of, and there's going to be two in this case, provided that matrix has full rank, which obviously it does because of that. Okay, so there's going to be two vectors that span, and it's going to be rho cos theta d by dx plus rho sine theta d by dy plus d by d phi. Okay, so that one will be in the here we go. Okay, and then the other one, x2, and that one's kind of obvious just because there's zeros here. Okay, so that's d by d theta. All right. Okay, so and physically these are interesting, right? So so these are vector fields. So first, let me write down the big fact here is that the dq is spanned by x1 of q and x2 of q. Okay, and so this implies that d, and so in this case it's also true that d is smooth and locally constant rank. Okay, it's smooth because I have a vector field, namely x, which is smooth, right? The coefficients of x are smooth, it has rank 1, because it takes one vector field to form a basis for D at every point. And similarly here, D is smooth and locally constant rank. Okay. So smoothness is very, very common. Local constant rankness can fail to happen sometimes. Okay, so that one you do have to watch out for. Okay, now physically, these vector fields have meaning. So let me talk about what they mean. Okay, so these are vector fields which span the distribution. So that means at every point, the tangent vectors prescribed by those vector fields lie in the set of admissible velocities, okay? And so what that means is that the integral curves, right? So we talked about integral curves and differential equations, right? So the integral curves of those will have tangent vectors which satisfy the velocity constraints, okay? And so it's interesting to think about what are the motions of those two integral curves. Well, they have very simple explanations in terms of the physical motions of the disk. This obviously is just the disk spins. Okay, so d by d theta, if you think about the coordinate theta, it's the rotation about the s3 axis. So x2 is the spin motion of the disk. And similarly, if you fix theta, okay, then x1 is the, it's got to be very annoying because I'm writing things and they're not showing up on the screen until 45 seconds later. So if you fix theta, okay, then this describes this. Okay, that's the point. Okay, good. All right, so these are two examples, and you can explicitly and simply calculate what these spanning vector fields are in this case. Okay, good. Something that we mentioned last time, but now let's talk about it a little bit more carefully, right? So in these two, okay, good. And that is that in this example, the velocity constraints are such that really, although we have a two-dimensional configuration manifold, really the configuration manifold is one-dimensional, okay? And that's because in this equation, you can just integrate this equation, right? And if you integrate that equation, what it does is it gives you x as a function of theta, right? And so really that two-dimensional configuration manifold with a one-dimensional velocity constraint, that really ends up with a one-dimensional configuration manifold, okay? Now in this example, it's not so easy to see what's going on. So I have a four-dimensional configuration manifold, x, y, theta, phi, with two linear velocity constraints. Okay, so is there really just a two-dimensional configuration manifold there? Well, no, there's not. And how can you tell, right? You somehow think that it shouldn't be that way, right? And this is, so let me maybe give the definitions here, and then we'll talk a little bit more, okay? So this is what's called integrable velocity constraints. Okay. All right, so a velocity constraint. So sorry. Is integrable if, okay, for every q in Q, there exists a submanifold. And so it's not quite necessarily a submanifold, but I'm not going to fuss with the details of it. Strictly speaking, it's what's called an immersed submanifold. It's not quite a submanifold corresponding to our definition, but maybe I'll just hurdle over that little technicality. So if there's a submanifold, and I'll call it lambda of Q, such that first, Q is in lambda. Okay, so pretty soon you'll see that Q is in lambda. There we go. Okay, and the tangent spaces to lambda, okay, so these are subspaces, of course, of the tangent spaces of Q. Are such that these tangent spaces are actually equal to the subspaces specified by the distribution. Or sorry, the linear velocity constraint. D is also called a distribution, and distribution is a word which is greatly overused, and this has nothing whatsoever to do with distributions that you would have learned about last year in 332.5, whatever. Okay. Okay. All right, so there's a picture there, and I'm going to try to draw the picture. Okay. And the reason I'm going to try and not necessarily succeed is that it's a three-dimensional picture in order for it to kind of have resonance. Okay, so here's our three-dimensional Q. Okay, so I'm pulling out a little chunk of it. Like so. Okay. All right, now let me take a point Q in Q. So Q, the point I've drawn is inside that blob somewhere. Okay, and at Q, there's going to be some subspace, which is, so this is Q, and this is DQ. Okay, and so the idea is that Q is three-dimensional in this picture, and when it shows up here, yeah, there we go. D is two-dimensional. Okay. And so the way you should think about what's happening with an integrable velocity constraint is that I have a submanifold, a two-dimensional submanifold, or yeah, a two-dimensional submanifold lambda. So that's going to be like some slice of Q, like so, and DQ. So DQ is equal to the tangent space here. Okay, right. So this in yellow is lambda. Okay. Oops. There we go. Sorry. Okay. All right. And so that's the picture you should have in your mind of an integrable velocity constraint. And so an integrable velocity constraint, the point is that an integrable velocity constraint isn't really just constraining the velocities, it's actually constraining the configurations, because the configurations are required actually to move on this two-dimensional, in the drawing, two-dimensional submanifold lambda. Okay, so the idea is that for a linear velocity constraint, the motions must, so let me say the motions through Q must lie on the submanifold lambda. Okay. All right. Okay, so that picture corresponds to the first example, the disk rolling in a straight line, right? So that lambda there will be the one-dimensional submanifold that describes the motions of the body through a given x and theta. All right, and so a linear velocity constraint d is, well, non-integrable if it's not integrable. Okay, so this seems like a fundamental difference or a fundamental dichotomy with velocity constraints, right? So if it's integrable, that gives you a very, that you're not just constraining velocities, you're constraining positions, okay? And so somehow you'd like to be able to detect that. Okay, so you don't want to have to try to find this submanifold lambda. Maybe you can do it, maybe you can't. But you'd like to at least maybe be able to say when a linear velocity constraint is integrable and when it's not. And it turns out that there's a simple way you can check that. Okay, so to test integrability of a linear velocity constraint d for Q in Q, a subspace. Okay, and I'm going to call this subspace L of D at Q. Okay, and this is going to be the span of a collection of vector fields, and I'm going to tell you how to build those vector fields. Okay, so what you do is you take, so we talked about Lie brackets. So this has to do, interestingly, and I'll maybe try to give some insight into why this is the case, but it involves Lie brackets. So here's the construction that we're going to do. We're going to go x1, x2. So we're going to construct a Lie bracket. This is going to be xk minus 1, xk. Okay. So this is going to be a Lie bracket of length k. Okay, so I'm going to take xk and xk minus 1 and xk here. Here. There. Okay. And I'm going to take the Lie bracket of them, and then I'm going to take the Lie bracket of those ones with xk minus 2 and all the way out to x1. Okay, so that's a thing you can calculate in principle. Okay, and what must these vector fields satisfy? Okay, so these vector fields, x1 up to xk, so they're smooth vector fields, of course. And they satisfy that xj at q okay, so I have to find vector fields whose tangent vectors lie inside D, of course, that totally makes sense. And I also, what's K? So K is unrestricted. Sorry. Okay. All right, so that's a calculable thing in principle. You just take some vector fields x1 up to xk that span each of the subspaces D. Okay, then calculate a bunch of Lie brackets, and then take the span of all of those, and that's this subspace LD. All right, so I'll calculate this in the examples. Okay, but for our purposes, the interesting thing is the following theorem. Okay, so let D be a linear velocity constraint. And there's two cases that I'm going to consider. So if D is smooth and locally constant rank, and if L of D of Q is equal to DQ for every Q, okay, then D is integrable. Okay. Now this condition, if you think about this condition for a moment, okay, so this condition seems to say that I need first to calculate LD, and I need to calculate all these brackets, Lie brackets of length K. Okay, but you don't actually need to do that. Okay, if you think about it for a second, because L of D is equal to D, it suffices to just take single brackets. So if it's the case that if you take two vector fields, let's say x1 and x2, okay, and you take the Lie bracket of those, and the Lie bracket is in D, okay, so in the linear velocity constraint, okay, for any vector fields x1 and x2, which are in D, then you're done. Okay, because then you'll immediately have this condition, right? Because then if you just recursively apply that definition arbitrarily but finitely many times, you're not going to do anything different. Okay. All right. The other condition is a little bit stronger, but it involves a concept which we haven't really talked about, but I do want to mention it since it's important. And that is if the D is real analytic. Okay, so what does real analytic mean? Okay, so we know what smooth means. Smooth means that there's a bunch of vector fields that span D at every point in a neighborhood on Q. Okay, what does real analytic mean? Well, Real analytic means that rather than the vector fields being smooth, they're going to be real analytic. Do you remember from 281 the difference between real analytic and infinitely differentiable? So do you remember in 281 a function that looks like this? If you talked about it, apparently you've forgotten, and that's okay. So this is an example of a function which is which is infinitely differentiable, but it's not real analytic. So what does real analytic mean? Well, real analytic's rather like complex analytic. So one of them is that the function is equal to its Taylor series, right? So that's a property or a definition, depending on how you go at it, of a complex analytic function is that in a neighborhood of every point, it's equal to its convergent Taylor series. Okay, and real analytic has exactly the same definition. So a function is real analytic if at every point there's a neighborhood where the function is, where its Taylor series converges and the function is equal to its Taylor series. Okay, so this function here, if you calculate this function, all the derivatives of that function at 0 vanish. Okay, so the Taylor series of that function at 0 will be 0 because all the coefficients in the Taylor series, which are given by the derivatives, are 0. So the Taylor series is 0, but the function is not 0 in the neighborhood of 0. Okay, so anyway, that's what real analytic is. Okay, and the reason I care about that is that if D is real analytic, then it is integrable but actually necessary. Okay. Okay, so this gives us a way to check whether a linear velocity constraint is integrable. So in other words, when a linear velocity constraint is actually a constraint on the configurations and not just on the velocities. So let's check this in examples. Okay, so for this one, okay, so we had x is rho d by dx plus d by d theta. Okay, all right, so what we have to do to check to apply this theorem is we have to start calculating some Lie brackets like this. Okay, now this is very uninteresting in this example because there's only one vector field that I need to check, and that's x, because D is spanned by x. And so if I'm going to check this condition for all vector fields which are in D, sorry. All right, so if I'm going to check the condition for all vector fields which take values in D, there's only one vector field to work with, and that's x. Okay. And so LD, okay, is spanned by Lie brackets of x with itself. But remember what the, there's two versions of the Lie bracket that I'll give you. One is the actual definition, and that defines the Lie bracket as a derivation. So remember that the formula was Lx, Ly coordinates, the Lie bracket looks like this. So I'm using Q's here. The only thing I will draw your attention to is that this is skew symmetric. Okay, and so that implies, of course, that x with itself is equal to 0. Okay, and so therefore, that immediately implies that L of D is equal to D. Okay, because if this thing ever comes up here, okay, and so if the Lie bracket of x with the only vector field that spans C is x, the Lie bracket of that with itself is equal to 0, then I only need to worry about the case where k is equal to 1, right? Because it's just x and x spans D, and so therefore L is equal to D. That's the point. Okay, and so therefore we have the D is integrable. Okay. Okay. All right, good. So next time we'll look at the other example because that actually requires a little bit of computation. Okay, so we'll look at the other rolling disk example next time, and we'll see that that linear velocity constraint is not integrable. And hopefully the hardware will be working better next time.